Thank you very much for invitation. 영어로 해야 됩니까?
Do you want English or? Yeah.
Okay. So today I'm going to talk about proper. Okay, proper holomorphic maps between bounded symmetric domains. So okay, let's start. So the motivation to study this project is to study property of Hermitian symmetric space. So first, let me introduce what is Hermitian symmetric space. So in Riemannian case, we know symmetric space is very important object, and like Riemannian case, we consider in complex case Hermitian symmetric space. So X is a complex manifold with Hermitian metric. Then X is called Hermitian symmetric space, simply HSS, if at each point there is a holomorphic isometry that fixes X and reflect tangent vectors. This sigma X is also called involution, like Riemannian geometry. Any Hermitian symmetric space is factored into compact type, non-compact type, and Euclidean type. So, and this decomposition is unique, and this is today's topic. Now, every Hermitian symmetric space, even though metric is just Hermitian, actually it is scalar. And moreover, this admits unique Kähler-Einstein metric. So this is not just any Hermitian metric, but it's Kähler-Einstein metric. And this compact type has non-negative holomorphic sectional curvature, which means so semi-positive sectional curvature, and non-compact type has non-positive sectional curvature. And this Hermitian symmetric space is homogeneous, and the homogeneous action comes from isometry group. And this is Lie group, so by Lie group theory, we can make a pairing with compact type and non-compact type, so that any non-compact type is embedded into compact type as open set, and its automorphism group of non-compact type is a subgroup of automorphism of compact type. So this pairing is called duality. So since this is an open set, we call this as domain. So today's topic is bounded symmetric domain. And like symmetric space in Riemannian geometry, Cartan also classified all bounded symmetric domain. And there are 4 classical cases and 2 exceptional cases. So this type is called type 1, type 2, 3, 4. And this is 5, 6. So in any case, there is a concept of rank, which I will tell later. So today we will focus on this first time. Okay, bounded symmetric domain admits compact quotient. So that's a very special property of bounded symmetric domain. So not many domain admits compact quotient, but in this case we have compact quotient. And like Riemannian case, there is also strong rigidity for complex structure of compact quotient. So CU proved that M is a compact quotient of irreducible bounded symmetric domain, and if, of course, there is a Riemann surface, so we exclude Riemann surface, so dimension is greater than 2. Then the complex structure of X is determined by homotopic type. So if X is homotopy to M, then their complex structure is the same or just conjugate. So that means the complex structure is unique. And there is also metric rigidity. This is by Mock. So in this case, we need a little more. So rank is greater than 2. Let me tell you later about rank. Okay, M is a compact quotient of bounded symmetric domain, and rank is greater than 2. Then, and suppose M has another Hermitian metric with non-positive curvature, then this G is just a constant multiple of canonical Kähler-Einstein metric. So that means M has basically one Hermitian metric with non-positive curvature. So from this, we can see that if there is a two compact quotient of bounded symmetric domain, and if there is a holomorphic map, non-constant holomorphic map, then we can pull back this metric to M. This canonical metric M pull back to M is another Hermitian metric with this property. So that means this F is, of the constant F is just an isometry because there is only one metric here. So F is isometry, and not only isometry, but it's totally geodesic isometric embedding. So from this, we can see that M, this compact quotient, has very rigid property. And we can ask the same question about other quotient. So M is compact quotient, then we have very nice rigidity. So if M is another quotient, for instance, finite volume case, can we obtain the same rigidity or not is another interesting question. So like compact case, we lift map to their covering space. And of course, the lifting is not always proper, but in many interesting cases, lift is proper. So we want to study proper holomorphic maps between bounded symmetric domain. So now I'll consider rank 1 case. Rank 1 is just a ball. So unit ball is the only rank 1 case. So in this case,
랭크는 뭘 말하는
네,
랭크가 뭘 말하는
랭크가요. 랭크의 정의가 있습니다. 랭크라는 거는 이제 there are four here. This is exceptional. I don't know about this one. So here four classical case. Then each case we can consider how many complex torus, real torus in this space. So the dimension of maximal torus. Yes. So in this case, type 1 case, we have if the minimum of this number is rank. Okay. So sphere.
호모지니어스 스페이스로 봤을 때 그 네 그룹의 랭크하고 마찬가지.
네, 똑같습니다. Okay. In both case, we can check that automorphism group is a subgroup of Pn. That means only fractional linear transforms are automorphisms. So like in disk case we use Schwarz lemma. So in this case we can apply Schwarz lemma in each linearly embedded disk here. So we restrict automorphisms to each direction, and at each direction we apply Schwarz lemma. Then we can see that only this fractional linear transformation can be automorphism. Schwarz lemma. Okay. So since we have some time, so let me briefly show this proof that's very easy. So one-dimensional case, we learned Schwarz lemma. So I will just choose simple. So this holomorphic proper, and F fixes the origin. Then F the absolute value is less than 1, and if it is exactly 1, then F is just a linear map. So this is Schwarz lemma. So we apply Schwarz lemma in higher dimensional case like this. So like a sphere case, we compose automorphism so that F is a self map. Then we can assume that F fixes the origin, like Schwarz lemma. And then we use unitary action, so so this is complex matrix now. So we can make this upper triangular, and also this. Then consider eigenvalues. Then for eigenvector we can apply Schwarz lemma. So each eigenvector must be absolute value less than 1, and we can apply the same lemma to inverse of F. So F inverse and F, those two have this property. So any eigenvalue must be absolute value 1. And then also this must be always have this, okay, let's call this distance decreasing property, because this is a map from tangent space to tangent space. So tangent vector must be, the length must be shrink. So this always has distant decreasing property. So for that, we have this diagonalizable map. And then, so okay, now consider any eigen space. Then F is like some kind of, so for instance, this is image of F. Then we project this map to this. So first consider this is just in C2 case. For simplicity, C2 case is like this. Then image is like this: F1, F2, and the eigenvalue is absolute value is 1. So 1 of 2. So this is eigenvector. So this must be C by Schwarz lemma. Then absolute value of this must be, so this ball goes to ball, so F1C 0 square plus F2C 0 square. This must be less than 1, but this is already C square. So in this case, so consider Z is 1, then this must be F2, C0 is 0. So on the boundary, this is 0, so it is always 0. So in any direction we have, this must OZ 0. So this is not a special direction, but any direction, so that means F is just an identity. So we can show that any automorphism group is a subgroup of this. Okay, so from this, so this is basically Schwarz lemma, but you can say differently. So in more, I don't know. In modern geometry, we can say that F, this automorphism, is a isometry of some nice metric. So as before we said that there is a unique Kähler-Einstein metric. So this automorphism becomes an isometry of this unique Kähler-Einstein metric. So that means this automorphism is always determined by the first jet at the reference point. So reference point here, we choose 0, so only unitary map. So this unitary and product of automorphism, that's everything. So in automorphism case, we use metric, unique Kähler-Einstein metric, to get some kind of PDE, the first order PDE. And how about proper holomorphic maps? So in proper case, this is isometry. This
프로퍼라는 게 인버스 이미지 컨텐트 말하는 거예요?
네, visual sense에서. 네. So proper holomorphic map is not always isometry. So in this case, we cannot use this complex, this canonical metric. But if F extends to the boundary, then proper holomorphic map preserves boundary. So we can use.
BN이라는 게 오픈볼 말하는 거예요? 아니면
네?
클로즈볼 말하는 거예요?
BN이요? BN은 오픈볼을 말하는 거고요. 만약에 이게 바운더리까지 확장이 되면은
모든 게 오픈은
네, 프로퍼 네.
오픈이니까.
네. So this proper map always not always extendable, but if it is extendable, then we have better we have some rigidity. This rigidity phenomenon first found by Poincaré, and later we can use Tanaka-Chonmoja theory to get rigidity. So let me explain briefly. So if f extends smoothly to an open piece of the boundary, and if n is bigger than 2, then f is also linear fractional transformation. So only automorphisms. So here, in this case, we use metric inside, but here proper holomorphic map is not isometry, so we construct PDE on the boundary. So we briefly show how to use boundary structure. So in B2 case, for simplicity, sphere is boundary. So, and we choose this conjugate holomorphic vector field, which is tangent to S3. So if this 2 is usually called Cauchy-Riemann operator, and since L is tangent to the boundary, we call this as tangential Cauchy-Riemann operator. Then take bracket, then this generates another vector field. This is not Cauchy-Riemann because we have W and DZ, and also this is imaginary, so this kind of vector field also appear here. So anyway, this tangent space, this is three-dimensional, so we have three complex vector, L, L bar, and T. And T bar is just a constant time of T, so we have three linearly independent complex vector field. And choose, this is important, so we choose real part and complex part of tangential Cauchy-Riemann operator, and we call this as CR structure. So CR stands for Cauchy-Riemann. So for short, this we call Cauchy CR structure. Then we differentiate this equation. Since f preserves boundary, so on S3, this map satisfies this simple equation. Then since f and g is an extension of holomorphic function, so we apply Cauchy-Riemann operator, then this must be 0. So we apply this to this, then we have this equation. So we have two equations here and here. So we write this as some kind of matrix form. So together we have system of equation. Then f and g is take inverse of this. Then f and g is just a function of this. Then now differentiate this again by L bar. Then we can differentiate right hand side again. So here this is first order, and we have second order here, but we conjugate this vector. So take bracket, then this must be 0 because this is complex conjugate of holomorphic function. So this part goes to 0, so we only have this, and this is t, just t. So here we have just first order linear PD, non-linear actually, first order PD. Then we apply L bar again to get here. The same is true, so we cannot increase order on the right hand side, but on the left hand side we increase order. So first, second order L bar 2 is determined by first order differentiation. So this is just one derivative of one vector field. So we have another vector field. So t does not appear. So we have to do similar thing again to obtain every higher order derivative is determined by lower order. So this we say that prolongate this further to obtain complete system. But how to prolongate? So that is a question. So to prolongate nicely, we have to see more about the structure. So let me show you later. But before then, we can ask similar question for higher order, higher dimensional embedding. So here from small ball to larger ball, we can collect all proper holomorphic maps. Then these two are equivalent if F1 and F2 is the same by automorphism actions. So image is in some sense the same. Then Huang and Webster first and later by Huang and Ji showed that if F extends C2 to the boundary and if dimension is bigger than 2 and big dimension is less than 2n minus 1, then F is just a flat embedding. We can do the same thing for this. Okay. And for higher dimension case, there is a counterexample. So many other counterexamples. And higher rank case. So higher rank case, there is strong rigidity. 네? Flat embedding. Flat embedding은 그냥 trivial embedding. 네, 그냥 네. 그러니까 G를 그냥 G0 이렇게 보내는 거 말하는 겁니다. So in higher rank case, if rank is bigger than 2 and the rank of the source is bigger than the rank of the target, then every proper holomorphic map is just a totally geodesic isometric embedding. So in higher rank case, rank is in some sense invariant, and then with this rank condition we can show that extremal disk goes to extremal disk, like geodesic goes to geodesic. So in this case, we can construct inside a PDE. But if rank is bigger, if the rank of the target is bigger, then we cannot use this extremal disk. So there's an easy counterexample for higher rank case. So recall that type 1 is just a matrix of this property. Then the rank is the minimum of these two numbers. So we define F to be, this is capital G. So the first factor is just identity, and we have one more left. So we just put any holomorphic function. Then obviously this is not isometry for any holomorphic map. So if rank become bigger, then there are infinitely many counterexamples. But this map is homotopic to trivial map. So if G goes to G, G000 is always proper, so we can make this to be arbitrarily small. So this image is homotopic to trivial embedding. So in this case, we can ask whether any proper map is of this type. So homotopic to this trivial embedding, G000, and this trivial embedding is always totally geodesic. So we can ask whether they are homotopy to trivial embedding.
When you choose a homotopy, do you require the homotopy itself be holomorphic or just topological homotopy?
In this case, this is just holomorphic.
Holomorphic homotopy.
But usually, if you just consider image, then just homotopy is okay.
G가 대문자입니다.
네, 여기 캐피탈 G입니다. 타이프를 잘못해가지고. So this is my recent result. So if F is a proper holomorphic map which extends smoothly to the boundary, so we want to use boundary structure. So we assume that F extends smoothly to the boundary, and here Q and Q prime is rank. So the rank satisfies this condition, then F is always of this type. And this condition is in some sense optimal, because if equality holds, then there is a counterexample. So counterexample is easy, we can write down, but anyway. So we study the boundary structure, which I call the shear structure before. So this is just an abstract theory. So let me focus on the boundary of bounded symmetric domain of type 1. So recall that type 1 is just, so here this is little g, but anyway. So this is a type 1 bounded symmetric domain. Then we can, this is complex matrix, so we can put this into Grassmannian by taking C into this matrix. So the PQ, this is an open set of Grassmannian. So that means the compact dual of this is Grassmannian. Then we define inner product. This is inner product with different signature, so we call this as basic form. Then this domain is nothing but any q-dimensional vector space such that this inner product is negative. And the boundary is nothing but this inner product has, so this is always negative, and then this must be q minus r negative and r zero eigenvalues. So that's boundary. So from r from 1 to q is the boundary of this bounded symmetric domain. Okay, and then we can easily see that this R becomes bigger, then set becomes smaller. So we have nice stratification on the boundary. And if the set is the smallest, then we call this Schirloff boundary. And if set is the largest, then this is a hypersurface boundary. So this is smooth boundary. So we see the boundary structure of this boundary. So take tangent space. Then tangent space is a subspace of Grassmannian, and this tangent space nothing but homomorphisms. So since we see that V has R zero eigenspace, and so V0 is the zero eigenspace, and V prime is complement, then we can choose frame, moving frame, like Riemannian embedding case, isometric embedding. We can choose moving frame adapted to this tangent space of the image. So we can nothing but we can choose a nice moving frame so that this image is nothing but this form. So then V0 is zero eigenspace. So this is the defining equation of the boundary. So we differentiate this equation to get this equation. This is the defining equation for the tangent space of the boundary. And this, we substitute this into this to get this. That means the tangent space, here only y appears, so tangent space is nothing but L, such that this y part is skew Hermitian. And then take holomorphic part. Then the holomorphic part is just a corner of this equation, and this is complex direction. So this is CR structure. That means the tangent space of this bundle spans tangential Cauchy-Riemann operator. So then, as before, we take bracket. Then this is just a simple bracket, but this is an important invariant, which is called the Levy form. And this Levy form is skew Hermitian, and sometimes it is degenerate. But this is some kind of, so since this is skew Hermitian, this is some kind of inner product on the complex direction. So we use this Levy form like some metric, but this metric is only defined on the complex direction. So, and this is also not non-degenerate, so this is degenerate. So we have to model out degenerate direction. So let's check what is the degenerate direction. Now we decompose tangent space into three parts. One is only y part appears, and this must be a tangent vector, so this y part must be skew Hermitian as before, and this other two direction is here the remaining of this, and then we can check that tangent space complex direction is union of this, and then this part is the common part, so we call T0, and on T0 we can check that V0 is constant, so that means the integral manifold of this distribution is this. So that means there is a complex manifold inside the boundary. So this is complex manifold. So that means the bracket of vectors must be vanished. Otherwise, it is not integrable. So since it is integrable, the Levy form degenerate on this T0. So we model out this direction. Then on this bundle, Levy form defines a positive definite form. So here we have some kind of a metric. Then, so this is the local version. So anyway, we want to prove this, but how? So if you study isometric embedding, then you know that the second fundamental form determines everything. Here it is quite similar. So we define second fundamental form on t plus and t minus. So that means t plus and t minus is preserved. So with this condition, we can see that t plus and t minus is always preserved. Then you can determine second fundamental form. This is not exactly t plus mod t0, because we have metric on t plus mod t0. Anyway, we define second fundamental form using that metric, and then check whether this second fundamental form is trivial. So that's not always trivial, but if this condition satisfies, then it has trivial solution. So with this condition, we have trivial second fundamental form. So that means complex direction on complex tangent space, we have some kind of trivial embedding. Then the real direction is left, but we can generate real direction by taking bracket. So that means complex direction actually determines everything. So that therefore every second fundamental form is trivial. That means embedding is actually flat embedding, and in flat that is proposition. So we have flat embedding. So this image is here. This is constant, and the image is actually is in here. So here it is flat embedding. Here we have complex manifold, but in complex direction we don't have any control. So here we have identity map. Here any holomorphic map. So finally we have this. Here we have constant, the first component. Second component is flat embedding, and third component is any holomorphic map into complex space. So, okay, that's it. Thank you very much.